In this video, we look at the energies and wave functions of the stationary states of the quantum harmonic oscillator. The wave functions of the stationary states satisfy the Schrödinger equation, minus h bar squared over 2 mu d squared dx squared, operating on psi of x, plus 1/2 kx squared times psi of x equals e times psi of x. The second term here is the quadratic potential energy V of x, and x is the displacement coordinate. When solving this equation and requiring that the psi solutions are normalizable, we see that the energy values are quantized. We get E of n equals n plus 1/2 times h bar omega, where omega is the oscillator frequency, square root of k over mu with the reduced mass mu, and n is the quantum number, 0, 1, 2, and so on. Only for these energy values do we get normalizable solutions for psi. Note that the quantum number n for the ground state is 0, in contrast to the particle in the box where the ground state quantum number was 1. This is purely a matter of convention. Let's plot the energy levels on a scale of E over h bar omega. The energies are, for the ground state, 1/2 for n equals 0. First excited state with n equals 1 has an energy of 3/2 h bar. The next state is n equals 2 and has 5/2 h bar omega as an energy, and so on. Two things stand out here. First, the energy levels scale with n, so they're proportional to n, and are therefore evenly spaced, with the spacing delta being equal to h bar omega. In comparison, the levels for the particle in a box problem scale with n squared. And for the Bohr atom, we found that they scale with 1 over n squared. Second, the ground state energy is non-zero. This is similar to the particle in the box. This energy is called the zero-point energy. It means that there is always some residual vibration in a molecule. You just can't stop it. Next, let's look at wave functions. They are given by psi of n of x equals an times hn of x times square root of alpha times e to the negative alpha x squared over 2, where alpha is an abbreviation for the square root of k mu, all divided by h bar. The expression for the wave function here contains three factors. The first factor is the normalization constant, and it is given by an equals 1 over the square root of 2 to the power of n times n factorial times alpha over pi to the power of 1/4. It clearly depends on the quantum number n. The second factor, hn, is called the Hermite polynomial. For the first few values of n, the polynomials are h0 of z equals 1, h1 of z equals 2 times z, h2 of z equals 4z squared minus 2. You can see that n determines the degree of the polynomial. The higher n, the higher the degree. Hermite polynomials can be generated easily using a recursion relationship that goes like this. H of n plus 1 of z equals 2z times h of n of z minus 2n times h of n negative 1 minus 1 of z. With this, you can, for example, take h1 and h2, plug it into this equation, and obtain h3. The third factor in the wave function is a decaying Gaussian. This factor makes sure that the wave function goes to 0 with increasing displacement. For the wave function, the quantum number n can be any non-negative integer, so there is an infinite number of wave functions. They consequently form a complete orthonormal set. Complete orthonormal set. This means that each wave function is normalized, that they are pairwise orthogonal, and lastly, that any other function can be represented as a linear combination of all of these functions. Let's plot the wave functions psi n and the associated probability densities psi n star psi n. Psi 0 for n equals 0 looks like this. It is a pure Gaussian function. It resembles a half-wave, except that it has exponential tails on the left and on the right. These tails penetrate into the classically forbidden region. The associated probability density has a similar shape. Psi 1 for n equals 1 contains a linear term in a Hermite polynomial. The function looks like this, therefore. It consists of two half-waves with exponential tails again on the left and on the right. The probability density looks like this. For higher n, it continues in similar fashion. For example, for n equals 2, the wave function looks like this. And the probability density looks like this. The higher n gets, the broader the wave function becomes. What does this mean for the vibration in a diatomic molecule, which was our original reason for developing this model? The wave functions are given in terms of displacement, x. So let's sketch an atom, fix it in space, and attach the other atom, let it move. The wave function then, in terms of displacement, is centered around the equilibrium length of the bond. It looks like this. It tells us where we can find the other atom. Clearly, in this ground state here, the atom is not completely localized. There is uncertainty associated with its position. If we measure its position, we will find it somewhere within this region of significant probability density. Also, the momentum is not completely zero, and the particle moves. This is very different from the classical case. There, a particle doesn't move in the ground state. For a quantum particle, this is not possible. It cannot rest. Even in the ground state, it has residual energy and residual motion. Let's look at the first excited state. Again, we fix one of the atoms, and we look at the other atom in equilibrium position and plot the probability density. It is likely that we find the atom at the position left or right of the equilibrium position, but never directly at it. This means in this state, the bond is either shortened or prolonged, but never exactly at equilibrium. In summary, we have looked at the energies and wave functions of the harmonic oscillator, and at how to picture them for vibrations in a diatomic molecule.